Good afternoon. Here we are, ready for this lecture. Go on with the record and let's share the presentation. Okay. Okay. So this morning we discussed the possibility of interpolating the aerodynamic matrix. In particular, we okay, just a second. Okay, we proposed this alternative approach for the solution of this equation, which is also known as flutter equation. This equation is the key equation for discussing the stability of an elastic system. And if you take the determinant of this equation and consider the condition of determinant B0, one can evaluate the poles of the system in such way, and then one can demonstrate, and we will this not today, maybe today or tomorrow probably, we demonstrate that the time solution of the free problem is regulated by this Sn coefficient, and therefore this Sn coefficient has the role of as a key role in the discussion of the stability for the system, as in the standard linear case for differential problem. But we don't have a differential problem, we have an integral differential problem. And so we have just to define and better clarify this point. However, we will this later, and we face the stability practical problem, which consists of solving this iteratively, this equation. And this is one possibility to solve with an iteration this problem. A second possibility is another path, another way, consists of approximating with an analytic form this equation. We know this matrix. We know this matrix as a black box for fixed value of S of omega, or P or K, which are the Laplace and Fourier quantity in dimensional and undimensional case. Okay, so we know we can call as a subroutine this matrix for evaluating this matrix for each value of S. So we could approximate by means of an interpolating form this matrix, and we show practically a couple of possible approximation. One is known as approximation 1, like this, or another kind of approximation like this, approximation number 2. And this approximation in general may be evaluated minimizing the error between the data provided by a computer and the interpolating structure assumed. As a result of this optimization problem, we have this matrix like this A2, A1, and 0 in this first form, or this other matrix in the other form, like the same A0, A1, A2, and P and R, which are the alternate or alternative matrix with respect to the other case. However, in both the cases, we have a common polynomial structure with A0, A1, and 2. We have this common structure in these two variants because we are convinced that this matrix has this kind of a polynomial approximation because the theory says to us this, okay? And we have also commented the fact that if we assume one of this polynomial structure and we include this definition in the equation of flutter for linear aircraft, we have the possibility to define a new state space variable by considering the proper part of this, the proper fractional part of this approximation, as denoted here as yellow, the yellow part. This yellow part can be, which is a not proper fraction, because we have a level, a degree 1 at the numerator for S and degree 1 at the denominator for S in this case. We can perform this division and we can obtain at the end this, after the division, this structure, this final structure, and then this here could be the new state space variable like R. And after organizing everything, we have at the end a unique state space matrix refer to this unique state space vector. In this case, the elastic system analysis stability can be performed in the standard way, just taking the standard eigenvalues of the matrix A directly. So in this case, the flutter stability analysis can be directly performed by finding the eigenvalues of the matrix A and the corresponding eigenvector, of course. This is what we found, and we have also did tomorrow morning a final connection between this approach and a similar approach that can be performed for the 2D airfoil theory, analytic theory by de Dorsen, and this technique allows to approximate the Theodorsen function C like by using a fractional form, exactly like in the way we did for the rotational part of our operator. Note that the analytic theory of Theodorsen give a very similar structure to the interpolating function we assumed, like this. We have a polynomial part and we have a not polynomial part. In the Theodorsen theory, we have a polynomial part in Laplace domain, of course, a not polynomial part given by the Theodorsen function. And so for the not polynomial part, we want to assume a fractional part, a fractional approximation of the Theodorsen function, exactly like before. And in this approximation, we can denote and find the poles and the zeros of this approximation, which are apart the sign plus are this number here. And this number here can be performed again following an optimal criterion for minimizing the error between the exact evaluation of the Dorsen function as Bessel function, complicated Bessel function of key, and the value evaluated by using this interpolating form. Okay, so the approach is the same, and I ask to you to perform this approximation also in the exercise number 2, and this complete the performance of the exercise number 2. And so the exercise number 2, just to recap, this exercise is an exercise which required the following: required to study this flutter problem, a typical section flutter problem, by using by including this form for the aerodynamic, blah blah blah, and by considering both the exact form for the Dawson function and the approximated one. When you use the exact one, you have this generalized matrix, and you write your flutter equation in this way. Okay, in practice, this equation 10 is identical to this equation here, to this equation here, the flutter equation. Okay, this equation here, this is the general equation for a general aircraft, and this is the present equation for our section I4. And here we have mass, stiffness, structural stiffness, and we have all the aerodynamic term merged with the other one, the structural one, and the other, okay? And we have inside here also this transcendental part with CP. And we have this part in the general theory here inside the definition of E, of course. Okay? And so we have an identical problem. And for this problem here, we have assigned this parameter. We have assigned the mass ratio, the frequency ratio. This frequency ratio is the ratio between the omega alpha frequency by the omega pitch omega alpha frequency. And these two here are the offset, the distance between the 1/4 chord and the elastic axis. And this is the 1/4 chord and the center of gravity. And these 2 points here, I don't know, I don't have the typical session. Oh, okay, I don't know why I don't have. However, these offsets are assigned, and then an elastic analysis is required. First, assuming this as exact, and then do a procedure that I illustrate to you, assuming the exact expression for the Dawson function and the approximated one. When you have the approximated one, you have the capability of rewriting your system in a full state space form. And so you can compare the flutter limit found in the first and the second case respectively. Okay? Okay. In this exercise, just to complete the view of this exercise, we have this, for example, and this is a very interesting point. This is the point of the quasi-steady aerodynamic approximation. What I mean for quasi-steady aerodynamic approximation. And if you consider the formula, the final formula for the aerodynamic, we have, so for the exercise 3, we have understood the meaning of final state approximation, because also in the case of the Dawson theory, we have considered a added state. The added state is beta, as equal, as defined as the proper fractional part of C multiplied by the state space variable H, alpha, and so on. Okay, and this will give it to you a second order differential equation in time domain. So we have an added state, and an added equation. We have included a new state, a new equation. exactly as presented in the general theory. I want now also to consider a comment on possible aerodynamic model. I am talking about exercise 2. Comment on possible aerodynamic model. Okay. For example, when you have a process with a low frequency band, so you have a slow motion, you are considered not so fast motion of your airfoil. In that case, you may approximate your problem in a reduced band. You have the reduced frequency, and you know that your process is living here, just in a limited band from 0 to k minimum reduced frequency. In this case, you can approximate this, and the lower level approximation is the steady case. Steady means k equal to 0. So you may cancel this. K equal to 0 means omega equal to 0. So you can this. In particular, look, the moment is given to you 0. In fact, you know that the aerodynamic moment with respect to 1/4 chord is 0 in the steady Joukowsky theory. And in the Joukowsky theory of the airfoil, you have this as final result: no pitch moment with respect to 1/4 chord. But you see here that this is not true for a steady motion. If you have an unsteady motion, your moment time by time with respect to 1/4 chord is maybe not 0 at all. Okay. So in the steady theory, you have 0 almost everywhere. You have 0 here, 0 here. The only term is this term here. The only surviving term is this, and L steady means that the dorsal function C, as I told you, for omega equal to 0, is giving to you 1 real part and 0 imaginary part for 0 frequency. And therefore, in this limit case, you have C equal to 1, and therefore you have 2 pi rho u b 1, and again another u and alpha. And this is the standard expression for 1/2 rho u to the power 2 pi, which is the theoretical result for CL alpha for the airfoil theory. And you have a surface equal to 1 by 2b. This is the reference surface. And you have alpha, of course. This is the result for the steady theory. But we have also an intermediate result for a quasi-steady. What is a quasi-steady? Quasi-steady is something. Quasi-steady means that you not consider the acceleration, so the power by 2, because for a small k, a small omega, omega square is lower with respect to omega. Okay, so quasi-steady means include of course the steady part, but also this part here and this part here. Put equal to 1, C again, also in the quasi-steady case, green case, but you can avoid this, and you can include this here. And this is the quasi-steady approximation for the aerodynamic. Okay, of course, if you study the flutter problem in this case with our and you include the steady aerodynamic model for the aerodynamic and the fully unsteady model for the structure. What about the fully unsteady model for the structure? The fully unsteady model for the structure is a model, it's a standard model including the inertial force, which are of the order omega squared for the inertia and omega to the power 0 for the stiffness. And so if you use this equation for the structure unsteady and a steady behavior for the aerodynamic, your model is not consistent. However, this model was used and is used a lot in the application, but it can be correctly used only if you can say something of your bandwidth of interest. If your bandwidth of interest is a limited bandwidth like this, you may hope to include a model like this or a model like this. Okay, so the message is that in the practical application you may also apply or use intermediate model for the aerodynamic. And so this is the motivation of this request in the exercise. You have obtained the root logos in the case of quasi-steady aerodynamic, namely set ck equal to 1 and neglected the second order time derivative in equation 4 and 5, just as I did. And identify your flutter velocity and divergence velocity. The very last question in the exercise is important because this last question is deeply related to the fact on how applies this theory in an actual, this simplified theory in an actual aircraft configuration. You have a real aircraft. The question is, if you have a real aircraft, can you apply or use this simplified model for your real aircraft? The answer is yes, you can. And excuse me, I talk about this last, not this. I come back to this later. I have already discussed this because this question is exactly the analysis performed by including the added aerodynamic state, and then perform the stability just in the standard case. Okay, so I have already discussed this part here. The last part is interesting. Apply the present elastic model with unsteady aerodynamic to a general aviation aircraft. Instead, fly at sea level having a following characteristic: rectangular wing with chord equal to 1 meter, span equal to 4 meter, and half wing mass 80 kilogram. Okay, and moment of inertia respect to the line of mass centers 0.25 kilogram, axis center in this offset here, and first and second natural frequency of 8 Hz and 2 Hz. So after this, you have to do the following. In this application, we have do the following. We have to consider all this data, and you have to say, okay, considering this data, in my application, I have omega equal to the bending divided to the torsion. So this could be something like here and here. You have 8 divided by 15. Okay, so this is my omega. Okay, then I have to consider the mass ratio, and I have to divide this mass divided this air mass. And this mass is equal to the mass of the wing divided by the wing length. And so you can characterize your mass ratio as mass of the wing with respect to the mass of the air. Okay, and so on. You can evaluate the other parameters. You have everything for evaluating such parameters. And then you have your actual or practical wing here, and using this equivalence, you may transform this to this. And then evaluate the flutter. And this is the spirit of the last question. Okay? Okay. So I have completed this part. I have just to consider with you the point. I would like to have another comment with you on comment on Bernoulli theorem. In steady case. I would like just to have with you a connection, just a connection with previous study. Okay, and the connection is the following. Consider a let me consider the lift. The lift is by the standard definition is 1/2 for a thin airfoil So we have this airfoil x, y, and this is u infinite, and this is the flow, and you have a wake. Wake. Okay. We have that the lift is 1/2 rho u infinite, and you have the integral from the x to the leading gauge, x to the trailing gauge of the pressure jump. Why you have this? Because by the definition of lift or any kind of generalized force, you have that the lift is equal to the surface integral of minus pressure n dot k. K is the shape function associated to the lift, to the vertical rigid body motion. Okay, in this case is kappa. Okay, vertical rigid body motion. And in the case of thin airfoil, you have that this integral, which is a body integral up and down, and this is the surface integral around the airfoil. When you have a limit of this thickness going to 0, then this integral became, as you know, this integral became a surf bicircular into D to a line integral, just a line integral, excuse me, just a line integral of delta P. N by K is N, is 1, because the normal, in this case, the upper normal becomes 1. And when you take the circulation integral, you have just a jump upper and down. So you have not a circular, but a line integral now from X to the X at the leading edge, X at the trailing edge, but of the jump delta P in the X. Okay, so we have this quantity, we have, of course, the dynamic pressure. I forget to write the dynamic pressure, QD, okay? And the point now is, what about delta Cp? When we did the E3 theory, or the Bernoulli theorem, we found that in the steady case, this delta Cp in the steady theory is equal to minus 2 divided by u infinite, the derivative of the potential with respect to x. And here we have the derivative of the delta potential. And plus the unsteady part. Remember, here we have a part multiplying s or omega. And so in the steady case, this unsteady part is 0. So we have in the steady case, we have this, and therefore we have this definition for delta Cp. And so we have 1/2 rho u infinite plus 2 by u infinite, this here, and the integral from the leading edge to the trailing edge of the derivative with respect to x of delta phi in the x. And so we have L steady is equal to rho u infinite by delta phi at the trailing edge, because delta phi at the leading edge is 0. Remember that delta phi at the leading edge is identical equal to 0. And did you ever see this formula? Probably you have seen this formula in this form. Capital gamma. Did you or not?
Yes, the Gutta-Joukowski theorem.
Yes, this Gutta-Joukowski theorem. It's it. Okay. Just to remark that Joukowski theorem is valid in steady case, and the role of the circulation is delta phi. But it's obvious that this is gamma, because if you have we are talking about this airfoil, this wake. We have a delta phi, which is a function like this of x, and then it is steady on the wake. So this is the view graph of delta phi as a function of x. Look, this is delta phi. So delta phi here is 0 at the leading edge, and here the delta phi is not equal to 0. If you take the famous circulation line for phi and you take a circuit from here to here, okay, this is the delta phi. This circulation here is the integral of v dot dx. And in this case, this is not equal to 0, and this is equal to delta phi. Phi here, phi 2 minus phi 1. And what is this? This is gamma, the vortex. Which vortex? The vortex, the equivalent vortex, which is here in the place of the wing. Okay? And you have an equivalent vortex if you take this circulation integral in the other side, going to the I port and go here. Okay? Okay, so this is the story. This is another point I decide to give to you just to complete this scenario for the aerodynamic. Now I want to conclude this part on the unsteady aerodynamic. Just a second. Just a second. I want to conclude this part of the unsteady aerodynamic, sorry, by talking about lifting surface. What is this lifting surface theory? Oh, what did we do in on unsteady aerodynamic up to now? The point was the following: uncompressible flows, not viscous. 2, potential formulation. We discovered here, we discovered the wake. We discovered the contact discontinuity. Here we have presented our model in terms of pressure, velocity, physical variable in the stage 1. In the stage 2, we introduce the velocity potential, and we discovered the wake and its behavior with respect to phi. 3, integral formulation. 4, discretization of integral formulation. panel method. And 4, 5, build the generalized aerodynamic force matrix. So here we have coupled the potential flow theory issues with the structural dynamic issues, because now the body is moving, and the body is moving, the aerodynamic is unstable, and the pressure are a steady pressure, and then we have a steady aerodynamic force, and these steady dynamic force are exciting the structure itself, and we have closed the loop. We have fully closed the loop. So we have built this matrix as the E matrix. And this matrix is depending on S, and here 5, this matrix is decomposed in 4, 3. Porca miseria, ragazzi, non so cosa stia passando quest'ora. Giornata particolare. So we built this matrix as composed by this partial matrix, and 6, we have interpolation of GAF matrix today. Okay, these 2 points are also analytically calculated also by, in the 2D case, with the airfoil theory. And this is the Theodorson. And with the Theodorson theory, we can build analytically the GIF. We didn't give you the details of this theory, but we have the general procedure for evaluating the GAF matrix. And also for the Theodorson theory, we can interpolate not the matrix directly, but the Theodorson function. Okay, so we have done this up to now for the steady aerodynamic. Okay, I hope you are agree. Now, in this theory, in the analytic theory, the airfoil is thin. Here we have not thin body. We can model also the thickness of the body. We can consider also wing with thickness and bold body, a fuselage, and any kind of body, and the bluntness of the body is modeled by the source distribution in our integral formulation, okay? And the question in the very final point 7 is the following: any discount if we assume thin body, wing, and that's the reason of lifting surface theory. Any discount? Yes. The wake can be not considered in the discretization. Okay, and instead of building two separated matrices, E3 and E2, these two here, we can consider a unique matrix. Okay, and this is the very last point I want to talking about. Okay, so I want to consider this last point, and for team body, and I hope to have these two as the advantage here. Okay, and this will conclude our aerodynamic part. After this steady aerodynamic part, the fourth part of our course is flutter analysis, stability analysis and response analysis. I have all the instrument for perform the flutter analysis and response analysis of an aircraft. Okay? Okay. Uh, part this part here can be phased as the following. Let's consider now a body, a thin body. A thin body is something like this. This is the wing. Now the wing is a surface, and this is the wake. Okay, and these are our references axis. This is the x-axis and the y-axis and the z-axis. But now, as you can see, the body with zero thickness. Write our integral equation. We have our integral equation like 1/2 phi star equal to, but I want to stop now here because I want to give to you a break. 3, I stop. Thank you. Excuse me for the delay. No, 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 no. Uh, I'm. I have not said I want to discard the wake. I said if I consider thin airfoil and develop the theory, I realize that I can reformulate the theory directly directly connecting the pressure with the normal wash, skipping this intermediate step with the velocity potential. And in this unique formulation and matrix, we don't need to discretize the wake. I will show you in the next hour. Don't worry. I don't want to avoid the use of the wake. I want to show you that it's not necessary to discretize the wake in this case. Okay? This is different. Okay? Okay, so we can start our discussion, our lecture. Um, First, I have to share my screen. Okay, so I want to start just by the hypothesis that my lifting body is thin. Okay, this is my only hypothesis is this. I have a limit situation like in the airfoil of this, which is going to be like this, thinner and thinner and thinner. Okay. However, my integral equation is this. I consider a point here on the surface, and so I have this S body and the phi on the end, G minus phi dg in the end, ds, minus the integral on S body delta phi dg in the end dsw. Okay, so we are in Laplace domain, so we have tilde quantity for the unsteady quantity like this, and this. Okay, so what happened in this case? What happens is that we have originally a normal, but at the end I have as a limit process a line in section or a surface like this, and the normal, the upper normal here, excuse me, the upper normal here normal upper is equal to the opposite of the minus normal lower for the same x material point. Okay, and as we have already shown, this means that we have the same integral equation but applied to this to the discontinued, the jumped quantity. I have something like the delta phi dn g minus delta phi dg dn on this area, which is the area, the surface, the open surface of the body, and here we have the area of the wake. Okay, so this integral is on the area surface of the body, ds minus, we already have a surface in the wake, but now the body is just transformed in a wake-like body, just like a wake, because also the body, of course, is not permeable to the flow, and just like the wake. So we have the same equation for body and wake. In fact, this part here is going to zero because the jump of delta phi does not exist in the normal of the body. Okay, and so we have the same quantity for body and wake, and so we have a unique integral for body and wake together. So body wing union with wake. Okay, but we have a problem, Houston. I like this equation, of course, but what we have at the moment is an integral equation relating the velocity potential upper or lower related with the delta phi. We don't have anymore any condition on the unsteady boundary condition. Disappears. Okay, we don't have any information on the input, so we have to recover this information in such a way by using this equation. For this reason, now we want to take the normal, derivative and now normal means with respect to zeta, but zeta star with respect to zeta star. So, and in other words, I want to take the derivative of phi star with respect to zeta star. And we have this quantity just here in the left-hand side. So take this derivative. And so we have 1/2 the derivative of phi tilde x star with respect to zeta star, and this is on the left-hand side, equal to, what happens when we take the derivative of this right-hand side with respect to zeta star? First of all, this normal at the moment and in this limit condition is coincident. This normal derivative is coincident with a derivative with respect to zeta, not star quantity, but the normal now is zeta. Okay, so when you take the integral with respect to zeta star, the only quantity depending on the star variable are the G. Only G is dependent on star quantities. Therefore, we have minus, we have the integral on the body of the body surface and wake surface. We have surface only, and no dependency of delta phi by the zeta star quantity, but we have a derivative, a double derivative of G, one time with respect to zeta star and another time with respect to zeta. Yes. Okay. But do you remember the dependency of G with respect to the zeta and zeta star quantity? We have 1 on 2 pi, and we have R, and R is the square root of x minus x star power 2, y minus y star power 2, zeta minus zeta star power 2 square root. So the dependency of zeta on zeta star is such that the derivative with respect to zeta is equal to minus the derivative with respect to zeta star. And this is valid for any other space quantity because of this dependency. So let me use another page to be clear. We have that 1/2 p phi on the zeta star x star is equal to integral on a body, a wake, delta phi by second derivative of G with respect to zeta star to time in dx zeta. Okay, To be sharp, to be very, very sharp, I should use a limit here for considering, for keeping in mind that I have a limit process, which is this limit process here. This is the limit process for thickness going to be smaller, 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 up to this limit surface up and down. Okay, so here I should write limit for zeta star going to 0. Okay, we can introduce also dimensionless quantity. Quantities, plural, t's. So having an n-dimensional velocity potential, which is equal to the dimensional 1 divided by L infinite. We can introduce this is the normal wash key. We know this as key, normal wash. And this n-dimensional normal wash star evaluated in the star point is the dimensional 1 divided by u infinite, and then other dimensional quantity like x bar as equal by x by L. And we have also an n-dimensional green function. The green function dimension is of dimension of 1 on R, and so we have R by G as the n-dimensional green function. If we use this, we have this n-dimensional 4 giving the following: 1/2 key bar tilde star is equal to limit of integral on the awake a-body domain delta phi n-dimensional by the G n-dimensional by the zeta star 2 times n-dimensional dx dy. So this is our final, this limit of zeta going to zeta star going to 0. Okay, this is our very final reduced equation. Just a comment: the normal has become zeta direction because we have an airfoil in the plane zeta equal to 0. Our wing is at the moment a flat surface, and therefore the normal direction is the zeta direction. For this reason, instead of normal wash, somebody say downwash. How many people say downwash? I imagine that there are colleagues of mine saying downwash instead of normal wash. Okay, a downwash is the normal wash in the thin body theory. Okay. Okay. Now the very last process for you, and the very last process is a very final integration by part, which is the last part of my lesson today, the very final integration by part. I think that the integration by part, Gauss theorem, and related issues is the main mathematical physics concept useful for engineering. This is probably the second. The first one is the Taylor expansion, I think. I'm not convinced, I don't know. However, Gauss theorem, integration by part and related issues, main role in engineering. Maybe first position, our position. Second one, Taylor expansion. So everybody, let's integrate by part. And what I have to integrate by part? Start with 1/2 T bar tilde x star equal to, let me avoid this limit, the limit notation. So we have wake and body, delta phi by second derivative of g bar with respect to zeta star to the power 2. And I want to integrate fact, and I want first of all multiply these two quantity by 1. I want to see this one like the product E I k x bar by E minus I imaginary unit k x bar. This is the trick. And so we have to factor like this, integral delta phi by e to the power I k x bar. I have another factor, a to the minus I k x bar by the derivative of g with respect to zeta bar to the power 2, 2 times dy zeta. Excuse me, dx dy, dx dy. Do not forget, please, that we are integrating in this domain and this domain here. No, in this domain here. And this is my domain, wake and body. So remember that this domain will be discretized, and then I will discretize the equation I'm going to obtain just now. Okay, integration by part, what does it mean? I want to integrate by part, but I want to integrate by part only in one direction. Integration by part with respect to x bar quantity only. So the integration by part is concerning this variable, and I want to, in this process, integrate this. I want to derive this. So I want to integrate and derive. This is my scope. Of course, this integration is an integration in terms of no, it's not exact integration. It's only a formal integration in the sense of how do you say, the theorem of the extreme of the boundary of integration. As I show you, is better, it's faster. Okay, so I write the following. I want to integrate by parts, so I have a boundary term. However, I want to keep my integration. This double integration is an integration from the minus y2 plus y2. This plus y by 2, and this minus by 2 is the following limit of integration. We have this, which is plus y2, and this is minus y2, and this is y, the span of the wing. Okay, so this is the y direction. A capital Y is the span of the wing. So I want to keep this integral, so I have, first of all, the integral from y by 2 to y by 2 in the y. So I don't want to solve this integral, I want to keep this integral. And inside, I want to integrate by part with respect to x, and so this is the derived part, so I have to rewrite this delta, this factor delta phi by e to the power ikx, and I want to write the integral of this quantity, and I want to consider this integral in a formal way, and so I have plus infinite, which is an arbitrary constant, and this is the second edge of integration, like c, and I want to have e minus I k lambda dg with respect to zeta star 2 times, and I have here to integrate in d lambda. And at the end here, I have a function to be evaluated for xi equal to plus infinite and xi equal to the leading edge. Look, I have the x domain, and the x domain, I have the leading edge here, and I have the plus infinite here as x direction, okay? And therefore, when I integrate by part in this direction, integration by parts, I have a boundary term, this boundary term, to be evaluated in the second edge of integration and the first edge of integration. And this term to be integrated is the term composed by factor, which is the original term, and the term to be integrated. I have written here the integral of this quantity in the formal way. So giving this dependency on C just in this extreme of integration, and I have lost this quantity as arbitrary, as evaluated at plus infinite. Okay? So applying the integration by part, I will continue, and I have here minus the integral, same integral, minus y by 2 plus y by 2, and here I have to integrate from the leading edge to plus infinite, and here I have dy bar, and I have also the x bar inside here, and here I have to write the derivative of this term, so the derivative with respect to x bar of delta phi and e to the power ikx bar, okay, and the integral I have found. The integral I found is this integral, which we have found in the formal way, and is excuse me, is, where is it? Excuse me. Okay, I have the integral from plus infinite to x bar of e minus ik lambda dg second derivative with respect to zeta star 2 times, and we have dx dy. Note that this is the integral of this function, and this is the derivative of the other factor. Okay, and that's all. Now, first consideration: the boundary terms are equal to 0. In fact, here, what happens when you evaluate this quantity for zeta equal to plus infinite? When you evaluate this quantity for c equal to plus infinite, you have an integral from plus infinite to plus infinite, so this term is 0. And what happens when you evaluate the same term for c equal at the leading edge? At the trailing edge, you don't have any kind of discontinuity delta phi. And so this is 0 one time because this is 0, and the other time when this is 0. So we have 0 here, 0. We have only this part here. Okay, so let me rewrite this part. 1/2 key star equal to minus integral a wake a body derivative of the x of delta phi e to the power ik x, and this derivative is multiplied by this value plus infinite x e to the power minus k lambda jk lambda second derivative of g with respect to zeta 2 times, and this quantity is integrated in dx d lambda. Okay, now almost finished. We want to give a row of this quantity. What about this quantity? Do you remember the Bernoulli theorem? Remind the linearized Bernoulli theorem in frequency domain. In particular, we have that the Cp is equal to minus 2 jk d phi phi, and this part here is the part having the derivative of the velocity potential, but in the body frame of reference. So we have this plus this part here, which is the part related to the famous matrix D we introduced in the discretization, but we have a convective part of this derivative because we are using the computational frame of reference, which is a body frame of reference. But this is the Bernoulli theorem, okay? And what happens to the Bernoulli theorem for a thin wing? For the thin wing, we have just commented this part when we discussed the Joukowski's theory in the steady state. we have a jump of the pressure directly. We have directly a jump of the pressure on the surface. In any point, you have a jump, delta phi. Okay? Not a delta phi, and you have correspondingly a delta Cp. So we have a delta Cp, which is equal to minus 2 jk delta phi plus the derivative with respect to x of delta phi. This is the Bernoulli theorem. So try to take the derivative of this quantity. Better, try to develop this derivative here. Now, what is the derivative of x with respect to x bar of delta phi e to the power I k x? Easy. Develop this derivative. We have the derivative of the exponential, so we have ik delta phi bar x, of course, by the exponential. But we have also to derive the other delta phi, so we have the derivative with respect to x bar of delta phi. So this derivative is equal to this quantity, but this quantity is something similar to this quantity. In particular, this is the delta Cp, and therefore if you multiply this quantity by e to the power ikx, e to the power ikx, both sides, and if you multiply and divide it by minus 2, you have exactly this quantity here. And therefore, this quantity here is minus 1/2 delta Cp by e to the power ikx. And this is a very, very good news. In fact, our integral equation key star is equal to minus and minus sign are cancelled. We have 1/2. We have the integral on a wake and a body. And instead of this derivative, we can write delta Cp and e to the power ik x bar, and again multiply by minus infinite x bar e to the power minus j, or I if you prefer, k lambda, second derivative of g with respect to zeta star time dx dy. So I have a very final comment for you. We can cancel this 1/2. Okay, this is the minimum part. But we have the delta Cp. We have the pressure jump to be integrated. Where? On the body and on the wake. But the delta Cp on the wake is 0. Remember, this is a wake boundary condition. Here, delta Cp is identical equal to 0. And therefore, this is the answer to the question you have in the break. I have considered the wake, but the wake is not influent in this formulation. We can cancel this part of integral. So we have only an integral on the body. And this body integral is a body integral relating directly the downwash or the normal wash with the pressure on the body. So we have a E 3 by E2 operator. We have a unique operator relating pressure and normal wash. We have a unique operator. In particular, consider this very final formula. We have that our key bar tilde normal wash is equal to an integral on the body only of this delta Cp. I want to stress the dependency now for you to better understand. This Cp is a function of x and the reduced frequency, and this quantity is multiplied by a kernel kappa function, which is a function of x star, and reduced frequency to be integrated in dx dy. So x quantity, no star quantity. And here you have this normal wash, which is a function of x star and kappa, of course. Okay, and what about, so you have an integral relationship between normal wash and Cp. And your non-kernel function, this is known as a kernel function. This kernel function is analytically defined like equal to e to the power I k x bar integral from plus infinite to the present point x bar e to the power minus k lambda derivative of second of g with respect to zeta 2 times, zeta star 2 times, and this g is a function of x and x star as usual, but this is an error here, there is an error here in the, okay, we have a lambda here, lambda, and d lambda, and this is the kernel function. As a very final step, one can discretize in space what? The surface body only. Discretize in space, subdivide the body in panel. Attention please, panel only on a phase, not in a double phase, only in a phase. This is a surface. Is an open surface. So discretize in panels like this, only one phase panel, and we can allocate or collocate the solution in each panel, in the centroid of the panel. So we have key quantity in the panel tilde, in the panel n, is equal to, we divide this surface in panel, so we have the summation with m panel, 1 to m panel, and we have the integral on a panel surface m of the body, this for example, a m, and we have to integrate essentially the kernel function in the letting variable the x quantity and fixing the n quantity as x start quantity, and reduces frequency dx dy multiplied by the constant quantity of the delta Cp evaluated in the m point. So you have a linear relationship between an operator like A Nm, function of the frequency, multiplied by delta Cp M like Milan, summation Milan from 1 to capital M. So we have an operator relating downwash, excuse me, downwash and Cp. And therefore, we have that the delta Cp vector is equal to the matrix A to the power minus 1 applied to the normal wash vector. And this means that this unique operator A to the minus 1, the inverse of this matrix, has the same rule of A to the minus 1 as a function of K, has the same rule of the A3 operator by the A2 operator we found in the general case of a body with a thickness. And therefore, this is the result of this theory. This theory is known also as the lifting surface theory, or Vasinger theory in the steady case. For steady case, K equal to 0, you have that the steady value of the normal wash at 0 frequency is equal to the matrix A to the 0 frequency, giving you the delta Cp at 0 frequency. And this is the Vasinger wing theory that you probably know in the course of Professor Marino, probably. However, the magic thing for unsteady flow is that you can discretize the body only, also in the case of unsteady flow. Okay, you don't need to consider the wake, but the trick is that the wake trace are just in the kernel definition. Here you have to integrate. From plus infinite to x, and this is a wake contribution. So you have the wake contribution, but you have the wake contribution in analytical form. Analytic wake contribution, not numerical. Okay, and this is enough for today. We have concluded our lecture at 4 o'clock. I want to emphasize this point because it's the first time I finished in time my lesson. However, we have completed this scheme. We have considered also the special case of thin body wing. In the case of thin body wing, we have not a body with upper and lower panels. We have a unique flat surface with a unique panels like tiles distribution. And this is the theory implemented in Nastran. This is the theory implemented in the standard unsteady code for elasticity, ladies and gentlemen. Okay? And I concluded the story or the tales of aerodynamic, unsteady aerodynamic for aircraft. We have an operator, and we have also a simplified operator for our scopes. Okay, so see you tomorrow. Thank you for your attention, and If you have a question also tomorrow at the beginning of the lecture, please do, because we are in a focal point of our course. We have concluded all the modeling. Now we have just to find solution. We have the modeling. We have just to find solution. We present solution for different case. 3D structures, 2D structures, and so on. Okay? Thank you.
Sorry, Professor. Just a curiosity. Why the name kernel function?
The name kernel, on my knowledge, in the physical mathematics, is used a couple of times. One of this time is here. Okay. When you have an integral equation, this definition is inside the theory of integral equation. When you have an integral equation, you have to find an unknown, find fx such that ax equal to the integral of from here to here of g x y f x, excuse me, y dx is valid. You have an unknown. Your unknown is inside an integral in the x. This is an unknown. This is a known function. And this is a known function. You could say double. It's just like a double function. And this double function connecting your known with your unknown is the kernel function. This is the concept of kernel. In general, in applied mathematics. Okay? Kernel, known function. Okay? The name of kernel is also used in algebra, where you are considering a linear operator. And the kernel is the set of the value of, if you are mapping an x space in a y space, x space through a linear operator, there could be many values of x such that after the mapping give you 0. Okay, and this is also known as a kernel of the operator. The kernel of the operator is the set of the input giving 0. The kernel for a matrix is the non-trivial solution of the matrix. If you have a singular matrix, this is another concept of kernel. You have x, you have y, you have an operator. What about the x value such that ax is 0?
Yeah. In the algebraic case, I know the definition.
You know, but this is the role of kernel in the theory of integral equation. There is a theory, a general theory of integral equation. In that theory, the kernel is this function here. Okay? A kernel function is the green function for the source solution. Okay?
Yeah.
A kernel function is the pulse response in the time theory of the system. The pulse response h of t such that You have a delta Dirac as
Yeah.
a function
Yeah.
there. And this is function of t and tau, t and theta and tau, right? Okay, is a function of t and tau in the convolution integral. But okay, is another kernel function in time domain. Okay, expand your mind. Now you are the boss.
All right.
Okay.
All right.
Thank you.
Okay. Thanks. Afternoon.